Hello students. So today we are going to start dynamic consideration module 5 class 2. So in the last class we have discussed about the consistent mass matrix, lumped mass matrix for the bars, trusses and beams, and even for the quadrilateral asymmetric also. But the problem solving, so the problems based on we have bars and beams. Okay, so in the last class I have discussed about the bar, stepped bar, where two stepped bars are there. So using consistent mass matrix and stiffness of the bar. So using stiffness of the bar we have solved the problem. So today again we are going to solve same bar, so with a single bar. So let's start with the problem here. Eigenvalues, evaluate eigenvalues and eigenvectors of longitudinal vibration of the constrained uniform circular bar shown in figure. Take minimum two elements. So he is saying to consider the single bar into two parts. He has given the Young's modulus and rho, density of the material. He has given the length and he has given the diameter. Okay, so the FE model is given by, it's a circular bar divided into two parts. Okay, so I have drawn the FE model. I have three nodes, two elements. So I divide into two elements which I have three nodes. So area, how to calculate the area here? It is a circular bar, pi by 4 t square. So I just substituted the direct value of area A. Okay, so A directly I have substituted 3.14 into 10 raised to minus 4. Okay, fine. So now we shall start with the solving the problem. So how to solve the problem? Before solving this, I need to find the K. I need to find the equation Kx. Let me show the equation directly there. So this is the equation what I need to find here. K minus lambda m is equal to 0, where K is the stiffness of the particular component, whether it's a bar component or whether it's a truss component or it's a beam component, and m is a consistent mass matrix. So either we can use consistent mass matrix or lumped mass matrix, but I have explained what is the difference between those two. Consistent mass matrix will give you the accurate results, it will give the nearly exact results. When we come to the lumped mass matrix, we get very less accurate values, but difference is that if you go for consistent mass matrix, the complexity is more when the problem component or problem solution is complicated. But here we have a very simple bar, it's not too complicated, so I am going to use a consistent mass matrix. So this is the equation where we need to find. So for this equation I require the K value and M value, where K is a global stiffness matrix of the total component, whether it is stepped or whatever it may be, global of the K value and global of the consistent mass matrix. Okay, fine. Now we shall go to the problem here. So here the FE model is created. So next, for the first element, I am going to derive the K1 M1, where K1 is the stiffness matrix for the first element, K2 is the stiffness matrix, M1 is the consistent mass matrix for the first element. Okay, so because we have divided into two parts there, so element 1 and element 2, this is the first element. So A1 E1 by L1. So area in both the cases remains same because it is a uniform bar where we have divided into equal two parts there. Okay, so length we have 0.25, so divide by 2, 0.125. Both K value remains same, both K1 value and M1 value remain same because it is a uniform bar. Okay, so where K1 is equal to A1 E1 by L1. So I need not say the unit conversion there. 210 gigapascal is 2 into 10 raised to 9 Newton per meter square. Let it be in kg meters. Always the density should be in kg. Don't convert that into newtons. Okay, Fine. So here A1 E1 by L1, 1 minus 1 minus 1 1. This is a well known formula what we have for the bar element. So 210 10 raised to 9 into 3.14 into 10 raised to minus 4 divided by 0.125. Okay, if you need we can calculate here. So 2 into 210 into 10 raised to 9 into 3.14 into 10 raised to minus 4 divided by 0.125. So that gives us the value is what? 527.52 10 raised to 6 or 0.53, approximately 0.53 into 10 raised to 9. Okay, same thing if I calculate here consistent mass matrix, we have rho A1 L1 by 6. So rho we know, we can calculate here rho 7860 into 3.14 into 10 raised to minus 4 into 0.125 divided by 6. So this gives us the value 0.05. So this the total value gives us the 0.05 and this remains 2112, and I can multiply this 0.05 into 2 and into 112. Okay, fine, that we can do it. Okay, fine. So next this is the first element. So we have found the stiffness matrix for the first element K1, consistent mass matrix M1. Okay, so I said you for the element 1 and element 2 the stiffness matrix remains same because it is a uniform bar member. So equally we have divided, so the value remains same here, 0.53 into 10 raised to 9, 1 minus 1 minus 1 1, and M2 mass matrix of second element 0.05 2112. Okay, so here remains same. So now when you come to the global stiffness matrix here, so global stiffness matrix I have given the hint there in the previous lectures. So where this upper triangular matrix remains same in the first element, lower triangle matrix remains same in the second element. In the first element the lower diagonal value, in the second element the upper diagonal value, both are added. So here this portion, so here this upper triangle, lower triangle remains same, in the center it is added. The same way here the upper triangle 2 1 1 2 it should be there here, and here 2 1 1 2, here also 2 it should be there. So 2 plus 2 is 4 and remaining thing becomes 0. Or I have given even the what is that this is what I have explained. Now what I have explained, it's a thumb rule. Okay, so actually how we have to solve here is 1 minus 1 minus 1 1 if we have for the first element, and 1 minus 1 minus 1 1 for the second element. So how to make this global here is, for the first element we have element 1 2 1 2, and for the second element 2 3 and 2 3. So when I make it global, so here I have the matrix 1 1 1 2 1 3, so 2 1 2 2 2 3, 3 1 3 2 3 3. So now the same way I need to carry out here. So 1 1 horizontally 1 1, here I don't have 1 1, so this becomes 1. Here 1 2, here also I don't have 1 2, this becomes minus 1. Here 1 and 3, I don't have any connection between the node 1 and node 3, so it will be 0. Same as that 2 1, so 2 1 is minus 1. Now you observe carefully, 2 2, it's a 1 here, and again here also I have a 2 2, I have 1 here. So now I need to add these two, I will get 2, and here next is 2 3, so this is 2, this is 3, so this becomes minus 1. Now again 1 3 1, so I don't have anywhere connection there, this becomes 0, and 3 2, this is 3, this is 2. So how to check this horizontal vertical x y? So when I have 3 3, so horizontal 3 then vertical 3, then you have to match it. So this is 1. So now you can observe here, This is what I have here. The same way for the mass matrix I need to take here. Fine. Okay. Same thing, I got the global mass matrix. So this is a global stiffness matrix for the bar element, global mass matrix for the bar element. So I got two global K value and M value, I have got it. Now what I am going to do, now the eigenvalue problem is given by, now what is this eigenvalue? So eigenvalues gives us the natural frequency. So what do you mean by natural frequency here? Natural frequency, what do you call, but natural frequency is how can I explain? Okay, natural frequency is what? Free vibration of any elastic body are called natural vibration, and happens at a frequency called natural frequency. Example is what? Natural frequency is what? Frequency at which a body tends to oscillate in absence of any driving or damping forces. Like pendulum, once I push it, later I need not push, means I need not apply any force kind of thing. Very best example I'll give you. Pendulum, when you just pull it, it oscillates on its own. After some time, what happens? It stops. That is what natural frequency. But when you see the clocks, few clocks has a magnet. When you put a cell, what happens? When the clock is oscillating, on the ends you have a magnet where it pulls there. It just pulls. Means what? There is a continuation of oscillation. The oscillation never stops. That is not a natural frequency. Natural frequency is what? Once you put a load, once you pull it, or once if you give a force, later you need not put any continuous forces. If you leave to stop as on its own, so it oscillates at certain time and it will stop. That is the frequency what we call it as a natural frequency. So that is what? Free vibration of any elastic body, that I have given for the pendulum. If I consider ductile materials, free vibration of any elastic body are called natural vibration. Okay, fine. So this natural frequency can be found using eigenvalue. So why we require a natural frequency is in vibrations, in dynamic analysis, the vibration of a component is very important. Means at what frequency it is vibrating. Once we know the natural frequency of a particular component, we can easily design that particular component. Okay, so the eigenvalues are very, very important. These eigenvalues will give us what? Natural frequency. So today we are going to solve even the natural frequencies also. Fine. So eigenvalue problem is given by k minus lambda m is equal to 0. I said you how we got this equation. We got from the motion equation, mx double dot plus kx is equal to 0. From there we took it this k minus lambda m is equal to 0. Fine. Okay. So I know the k value. I substitute the k value here, and kx minus lambda mx, it is kx. So there is a small correction here. It's kx minus lambda mx is equal to 0. Okay, so where x is what? Deflections. Fine, Baba. This is q1, q2 and q3. So small correction, you can make their equation. So here this equation is kx minus lambda m into x. Okay, lambda m into x, where x is q1, q2, q3. Fine. Okay. So now I substituted the k value and substituted the m value. Okay, where I have the minus is equal to 0. Now boundary condition. What is the boundary condition at node 1? So you have saw the diagram in the beginning. It is a simple bar where one end is fixed, the left end is fixed. That is what? At node 1. So I have divided into three parts there. First node q1 is 0, therefore the characteristic equation. So here I am eliminating, I am taking directly the determinant here. So when I eliminate the first row and first column of the total equation here, this thing, and at the same time from the mass matrix. So I left with what? 0.53 into 0.53 into 10 raised to 9, 2 minus 1 minus 1 1, 2 minus 1 minus 1 1, here minus 0.05 lambda into 4 1 1 2. So after this I have took the characteristic equation. So to solve the lambda I need to go for the characteristic equation. What is the characteristic equation? Characteristic equation is determinant of k minus, sorry, so determinant is what? Characteristic equation is determinant of k minus lambda m is equal to 0. The same thing I wrote. I took only the k value and m value. So q1, q2, q3 I didn't took it because in the characteristic equation we need not consider that. Okay, so it is equal to 0. Now I am going to substitute these values here. So in the next slide, so here I have multiplied this 0.53 10 raised to 9 into 2 and this minus 1 minus 1. So I got these values including this lambda. So here I have multiplied and added here 0.53 into 10 raised to 9 into 2 minus 0.505 lambda into 4. Can you see here? 0.53 into 10 raised to 9 into 2 minus 0.5 into 10 raised to, sorry, into 4 into lambda. Same thing, 0.53 into 10 raised to 9 minus 0.505 into 1 into lambda. Same thing. So I have multiplied and added here. So finally I got this matrix. Now I am going to multiply this. So here I have I have added and multiplied all these values. I got finally this 1.06 into 10 raised to 9 minus 0.2 lambda. This value, total value, minus 0.53 into 10 raised to 9 plus 0.05 lambda. So here I took a minus common here. Here both sides I took a minus common. I got a plus value. Here also same thing. Both I took a minus. I got a plus. So here the minus remains as it is. So now how to multiply this determinant equation? The first multiplication is this. These two I have to multiply. So 1.069 into 10 raised to 9 into 0.5 into 0.53 into 10 raised to 9. Again minus. So 1.06 into 10 raised to 9. Why minus? This I have to multiply. This value and this value I have to multiply. So 1.06 into 10 raised to 9 into 0.9 lambda minus I have minus. So here I have. Later again this value minus 0.2 lambda into 0.53 into 10 raised to 9. Okay. Next minus of minus. These two minus of minus becomes plus 0.2 lambda into 0.1 lambda. Same thing. Now this is the first case what I have multiplied. Now second I need to multiply these two. Okay, so same thing here. So here both are same values I have. So into minus it becomes plus, but when I multiply these two I have to minus these two values. So with the minus value this becomes total whole square. 0.53 into 10 raised to 9 plus 0.05 lambda whole square I am going to get with minus sign. Here minus of minus it becomes plus, but in the determinant multiplication starts with minus. So this becomes a plus b whole square formula. Because of the minus everything becomes minus. Minus a square minus b square minus 2ab. Okay, because we have the minus. So for example, if I have a determinant x, y, z and r. If I have a determinant like this is equal to 0, I have to multiply x, y minus z into r is equal to 0. Okay, fine. So this is how this minus comes there. Okay, so here both minus becomes positive, then the minus remains there. Okay, fine. So now the same thing if I substitute the values here. So if I multiply this value I got this, and if I substitute this value with lambda I got this, and if I substitute this value I got this with the lambda. Here also same thing, I got the lambda square I got. So here I got the constant value, here with the lambda square and here with the lambda. So here now I am going to add lambda square values. First this and this both are lambda square. So when I go for the calculator, here I have the lambda square. So this is a 0.02 is plus and here minus 0.0025 is equal to, I got 0.0175 for the lambda square. When I go for the lambda, I have three values, this and last one. Okay, so these two are both are same I have, so this becomes minus 106 into 10 raised to 6 minus 106 into 10 raised to 6. Okay, and this value minus 53 into 10 raised to 6 is equal to, so I got how much? Minus 265 into 10 raised to 6. Now same thing, if I add the constant, so here this value and first value and this value, if I add it, so 5.618 into 10 raised to 17. So this is a minus of this value, minus 2.809 into 10 raised to 17. So finally I got what? So 2.809 into 10 raised to 7. So now I got the equation in the degrees form. So in the 2 degrees I have the equation. Now I can solve this using calculator. So I go to the mode. So in the mode where I need to find what? Equations there. Equation number 1. Under equation I have a degrees. So how many degrees? 2 degrees I have. 2. Now A, what is this A value here? This is A, this is B, and this is C, constant. So A value is 0.0175 is A value. B value is minus 265 into 10 raised to 6. And C value is positive 2.809 into 10 raised to 17. So I got what? X1 value. So X1 is 1.399 into 10 raised to 10, and X2 value is 1. When I go to engineer here, okay, 1.14 into 10 raised to 9. So this is 3, this is 3, this is 3. So total 9. So 1.146 into 10 raised to 9. So I got the lambda 1 and lambda 2. So now I got the eigenvalues. Now how to solve using eigenvalues? How to solve the frequencies? How to solve the frequencies of the bar or frequencies? So eigenvalues, from the eigenvalues, whatever the frequency you are getting, those frequencies are called natural frequency. Okay, so we know that lambda is equal to omega square, angular omega. So this is a angular velocity omega square. So this is the formula what we know from the vibration, mechanical vibrations. So already I have studied in the dynamics 2 chapters, 2 or 3 chapters, free vibration and forced vibration. There you will get it, lambda is equal to omega square. Therefore the frequencies are, we know that lambda is what? 2 pi f. Okay, because we have 2 eigenvalues, lambda 1 and lambda 2. First we shall solve with lambda 1. So I took lambda 1 and omega 1. Okay, so omega is 2 pi f. So I know the lambda value, lambda 1.399 10 raised to 10 is equal to 2 pi f whole square. Okay, so now if I substitute this value here, if I take this square on the other side, it becomes root there. So square root of, I take a bracket here, square root of this value 1.399 into 10 raised to 10. I'll close the bracket. So this is a square root and 2 pi comes there. So divided by, observe carefully here, divided by 2 pi. This is wrong. Why? Because 2 is different, pi is different. If you multiply like this, after this value divided by 2, then it will multiply with pi. So what you have to do, when you have the dividend, you have to divide each number there. Divide by 2, divide by pi. Okay, or you can put a bracket there. Divide by bracket 2 pi. However, okay, fine. So when I equal, I got how much? Sorry. So here it is an equation for let me take it in this regular form here. So if I take square here, once again I'll type it. It was in equation form, so it was taking the equations there. So I took, now I put it in a calculator form there now. So 10 raised to 10, I'll close the bracket, divided by, I can take bracket 2 pi. Okay, either you should use bracket or dividend. Okay, so now I got how much? 18824.74 Hz. So this is the frequency of the first one. For the same thing for the second one, if I want to solve, so here 1.146, only I have replaced this value. So I got is, sorry, something went wrong there. This is not 10 raised to 10, it is 10 raised to 9. Okay, this is 10 raised to 9. I got for the first value. So now I got what? 5387.8. Okay, so the same value for first frequency I got 18,824 Hz, and for the second I got 5387 Hz. Okay, so this is what the natural frequency. Once we know with this natural frequency, now we can easily find or easily design of this particular component. What do you mean by this particular component? So we have the properties, isn't it? Material density, rho, and Young's modulus. For these two type of material properties, so these are the frequencies or natural frequency we are going to obtain. Okay, fine, Baba. Okay, we shall continue further. Now we have found eigen values. Now we are going to find eigen vectors. So we know eigen vectors is eigen values we got 2, lambda 1 and lambda 2. So now we are going to find 2. First we shall consider eigen lambda 1. So this is the formula what we have: k minus lambda 1 m into x1 is equal to 0. I said you what is x1. X1 is the q1, q2, q3, but already we have eliminated the first one, first column, because it is a fixed end. Okay, so how we got this equation from the previous slide? So here in this equation, I substituted the lambda 1 value. Okay, Baba. So here 0.53 into 10 raised to 9 into 2 minus, or here both are same here, 1.06 into 10 raised to 9 minus 0.2 lambda you have, isn't it? Here lambda 1 value I have substituted, I got the numerical value there. Okay, fine. So here the same value I have here. So lambda 1, if I substitute 1.399 into 10 raised to thing, I got that. So one I will solve, one I will calculate here, this 0.53 into 10 raised to 9. This I need not take there because I have there directly in the previous slide. I have directly this value 1.06 into 10 raised to 9 minus 0.2 lambda. Okay, directly I'll put that value 1.06 into 10 raised to 9. Because this simplified, I have simplified form. This matrix simplified form here I have minus 0.2 lambda. So what is my lambda value there? 1.33 into 10 raised to 10. Fine. So I got how much? Okay, 1.7 I have. This is 1.6. 1, 2, 3 zeros. Okay, 1.6 10 raised to 9 I got. It depends upon the calculators, Baba. This is the old calculator. This is the old series. Some error will be there. So you will get 1.7. Okay, fine. So 1.7, 1.6. Nothing problem with the error. Okay. So this is, I got 1.6. You will get, if you use the advanced calculator or a new version of the calculator, you will get this value 1.73 into 10 raised to 9. Same thing you calculate for the others by substituting the lambda 1. We get this value. So now again the two equations are not independent because determinant of the matrix is 0. So this equation I can't solve because this values. So the 0 value, it is equal to 0. I can't solve this using any method. Now I am going to solve using a matrix method, or we call it as a eigenvalue, eigenvectors. So how to solve these eigenvalues and eigenvectors? So this In these two equations, I'll consider first equation. Why not second equation? Yes, you can consider second equation also, you will get the same solution. Okay, so we shall consider first equation minus 1.738 into 10 raised to 9 into Q2 minus 1.23 into 10 raised to 9 into Q3 is equal to 0. So here in this equation, I will convert any one of them in one form. Either I will convert Q2 in terms of Q3 or Q3 in terms of Q2. So here I am converting Q3 in terms of Q2. So Q3 is equal to some value into Q2. So how you will get here is, so this both are minus I have. If I take this value on the other side, so the minus remains same. So 1.738 into 10 raised to 9 divided by this value 1.23, not multiply, again divide, because this total value goes to the denominator, this into this. So or you can use the bracket there. So I am not using bracket directly, I am substituting there, is equal to. Okay, so can you see here 1.41 into Q2, the minus value remains same. So minus 1.41 Q2. Okay. So now thus I can write what? X1. So eigenvector is equal to Q2 comma 1 minus 1.41 Q2. So here I should write Q3. Instead of Q3 I have substituted the Q3 in terms of Q2. In the last previous problem, that is problem number 1, I said you to take Q2 is equal to 1. That you need not take. Directly you substitute Q3 in terms of Q2. I got eigenvector for the first X1 is equal to Q2 comma minus 1.41 Q2. Okay, fine. So next we have to go for normalization. So why we have to consider this? This is a standard thing to find the eigenvalue and eigenvectors we get from the mathematics. So x1 transpose m x1 is equal to 0. What m? M is what? M is a mass matrix. So where m we have here is what? This value 0.5 into 0.05 into 4. How much I got? This is the 0.2 value. This becomes 0.05, 0.05. This into 2. This is 0.1. So here 0.2, 0.05, 0.05, 0.1 I will get there in the eigen value. So here if I substitute the mass matrix 0.2, 0.05, 0.05 and 0.1. So this I got the transpose. So here what I have the x transpose. Sorry. Here I have x transpose. Q2 is minus 1.41. So anything Q2 minus 1.41 Q2. This is m 0.2, 0.05, 0.05 and 0.1. And x1 it is not a transpose, it becomes here. So in both the cases I will take Q2 common here. I will get Q2 square because here Q2 I took common, here Q2 I took common. I got Q2 square and this remains 1. So I said you how to multiply this matrix. So be careful with the matrix multiplication here. Always the matrix multiplication is possible. So this is how many rows and how many columns? I have 1 row, 2 columns. So this is 1 cross 2. Okay, this is 2 cross 2. And this is 2 rows, 1 column. 2, 1. Fine, Baba. However, I can multiply. I can multiply this, or this, and this. Okay. However, I can multiply because 1 into 2 or 2 into 2. Here both numbers are same. I will get 1 by 2 matrix. Or if I consider these two matrices, 1 into 2 or 2 into 1. So I got these two values. So I can have 1 by 1 matrix. However, I can solve, but better to solve what I do, what I am going to explain in the same way you try to solve. Okay. First we shall solve these two matrices. Okay. So this is one row, 2 columns. This is 2 row, 2 columns. Okay. Now how to solve this? 1 into 0.2 minus 1.41 into 0.05. So if I take these two values, what matrix I will get? 1 by 2 matrix. So 1 row, 2 columns I am going to get. So this and this I got this value. Again next same this and this. Okay, 1 into 0.05 minus 1.41 into 0.1. okay, if I substitute this value I got this, and if I solve this value I got this 0.1259 minus 0.091. okay, this matrix remains same. Again when I multiply these two, this becomes what, 1 cross 2, and this becomes 2 cross 1. So this matrix becomes 2 cross 1. So now these two are same. Now finally I will get 1 by 1 matrix, means one single value I am going to get. So here also same thing, 0.295 into 1 plus 0.091 into 1.41, minus of minus becomes plus, 0.091 into 1.41 is equal to 1. So if I solve this or if I solve this or simplify this, I will get 0.2571. So 1 divided by, so finally, so 1 divided by here value 1 divided by 0.25781 is equal to, I got some value here, Q2 square I have. So square root of the answer, what I will get, 1.9694. so this is the Q2 value I got. Now how to get Q3? Substitute the Q2 value here, 1 minus 1.41. so minus will get minus 1.41 into, so Q2 is 1.96. okay, so I got minus 2.76 or 2.77 I'll get. So this is the eigenvector for the first lambda 1 eigenvalue. For the first lambda 1 eigenvalue lambda 1, I got the eigenvector x1 is equal to 1.96 and minus 2.77. So next same thing we shall solve for the eigenvalue for the eigenvector for the lambda 2 is found from. So lambda 2 I know this equation remains in k minus lambda 2 m into x2 is equal to 0, where x2 is q2 and q3. Fine. Okay, so now the same equation, now I substitute the lambda 2 here in this equation. I got this same thing here. These two equations I can't solve because I have the value is equal to 0. I'll consider any one equation. I'll consider the first equation 8.31 into 10 raised to 8 q2 minus 5.87 into 10 raised to 8 q3 is equal to 0. In any one you put q3 in terms of q2. So how q3 is equal to, so this is minus I have, I'll put it on other side, this total becomes positive. Now it becomes 8.318 into 10 raised to 8 divided by, you can take bracket because multiplication you have, 5.87 into 10 raised to 8, close the bracket. So you got how much, 1.417 q2. So now I substituted q3 in terms of q2. So now what becomes eigenvector, x2 is equal to q2 1.417 q2. So for normalizing x2 transpose m, x2 is equal to 0. Same thing I have multiplied directly, I took q2 square common there. So I got this matrix. When I multiply these two, I got this matrix, and when I multiply these two matrix, I got 0.5424 is equal to 1. So finally I got q2 value is how much, 1 divided by 0.5424 square root of the answer. So I got 1.35, and if I multiply this value with what, 1.417, so I got 1.92. okay, so finally the eigenvector for the second eigenvalue lambda 2 kx is equal to how much, 1.35 into 1.92. okay, so this is how we need to solve eigenvector and eigenvalues. So eigenvalues, I said eigenvalues are found to know the natural frequency. Then eigenvectors, so eigenvectors so we can find, using eigenvectors we can find the mode shapes. So here we have the eigenvector values here. This is the first mode shape and second mode shape. So we can find easily what is a mode shape, how the shapes is deforming. So based on this mode shape we can easily identify what is a failure analysis. Okay, fine. So here for the first eigenvector, what we got here, is this thing. This is the first eigenvector. Second eigenvector we got is this. Okay, so for the first eigenvector, what we have here, so these are the nodes, node 1, node 2 and node 3, node 1, node 2 and node 3. Okay, so we have q2, q3, q2, q3, am I right? This is the first mode and the second mode, because it depends, the modes depends upon the eigenvalues, how many eigenvalues you have. Here we have two eigenvalues, two mode shapes we got here. So at node 1, you can observe carefully in both the cases, at node 1 it is 0. It starts from the 0, q2, q3. q2 is 1.92 at node 2, at node 3 is minus 2.77. So this is what the diagram where you can draw. This is the nodes, okay, and this is the use the displacement, how much it is displaced, okay, from 1. So there where we have a linear curve here. So linear curve we have. The same thing here, point at node 2 we have 1.35 and at node 3 1.92, where we have a positive in the second mode. So in the first mode we have the ups and downs, in second mode it is a linear line what we have. So by this mode shapes we can easily analyze the failure analysis. Okay, fine Baba. So today we have discussed the bar dynamic analysis of the bar, or we can say natural frequency or eigenvalues and eigenvectors of the bar. In the next class we shall discuss the beam. Okay, for your syllabus you have the bar and beam, truss you don't have. So in the next class we shall solve with a beam problem. So same using the beam stiffness matrix and consistent mass matrix of the beam. So here what happens when we consider the beam, the matrices will change. So where we have for the beam, each element I have 4 nodes, but when I consider the bar element I have 2 nodes. Why? The bar element is a 1D element, whereas the beam and truss elements are the 2D element. So definitely the stiffness matrix is going to change for the trusses and beams. For the beam, the stiffness value K value is going to change and consistent mass matrix is going to change. That I already discussed in the class 1. Okay, thank you.